messages, but right now we just want to focus on presentation here. Okay, so we're this is our video, perpetual motion video part 2, take 2. The first video was having trouble with the connection, so this time I turned off the Wi-Fi, and we're just going to use the phone signal. I have 3 bars of strength, which should be good. I also restarted the phone. Let's see how this works now. Okay, so let's start over. William, is that okay with you?
Yeah, that's
Okay,
fine.
so let's show the front of the book again. Okay, and then what I'll do is if it does it again, I'll just make a video and I'll upload the video later. So that way it's not depending on the signal of the connection. Okay, so please introduce us to this book.
Yes, this is the commemorative issue of Dr. Feynman's lectures on physics. These are a series of lectures that he presented while he was teaching at Caltech. Dr. Feynman is well known as a science communicator and a major physicist of the 20th century. The particular chapter of interest is chapter 46, which discusses the ratchet and the reversibility of mechanics.
William, do you want to be in the video, or is it okay? You want me to keep it on the book?
You can keep it on the
Okay,
book,
sure.
it's fine.
Okay.
And the chapter begins with an introduction for how the ratchet works. The ratchet, the idea is it's a device which only turns in one direction. If you imagine working on a car, you have the ratchet in order to take off the lug nuts, and they work in one direction to allow you to unscrew them and remove the tire. So
it's a tool, like ratchet as a tool, right?
Ratchet as a tool applied as a physics concept in this thought experiment. So
Great.
So you have the ratchet and pearl, which is, in terms of a simple machine, is a device which allows a shaft to turn in one direction. And the idea is to try and create a system which can extract work, given that you have 2 of the same temperature conditions as shown in figure 46.1. Now this would violate the second law of thermodynamics, that trying to extract work from a system that is in equilibrium, as shown in this paragraph down below, where it mentions this is inventing a device that would violate the second law of thermodynamics, generating work from a heat reservoir with everything at the same temperature. And it provides the experimental assumptions that you're assuming that T1 and T2 are both equal to each other, that they're both equal to T. And the idea is that because this is not taking place at absolute zero, there is molecular motion taking place. So the gas molecules would collide with this pane on this little shaft to the side in order to jiggle it in the directions. But because it can only go in one direction, given that this is a ratchet, the idea is it would rotate in only one direction. And based on this, the idea would be that it would do some work in order to lift up this object attached to the pulley. According to Carnot's hypothesis, this should not take place. However, by looking at this figure and knowing the thermodynamics, it seems like it should be possible. So let's evaluate this a little more closely and see if we have any problems. So this is an idealized system. We are assuming that the system is made of perfectly elastic parts, meaning that no kinetic energy is lost. It won't get converted to heat and lost to the universe, increasing the entropy. We're assuming that all energy is retained within the same system. And after the wheel turns a sufficient amount, then it should theoretically continue to jiggle until enough fluctuations take place that it sufficiently pushes it over to keep moving the ratchet. However, even with the gas continuing to rise in temperature in T1, the device will not continue on in perpetuality, according to Dr. Feynman, as stated in the bottom of page 46.1. Let's say the gas keeps rising in temperature along with the wheel. Does this process go on forever? No, and it goes into further detail on 46.2. Both both the wheel and the pole are going to experience Brownian motion, the seeming random motion of atoms as they bump against other things. And Brownian motion, it was explored by by Albert Einstein in his 1905 paper discussing the evidence of the existence of atoms, using it to, as he used it to prove the existence of atoms based on random movements of particles in fluids. So the so it's stated the reason the device does not work in perpetual motion is the vanes get jiggled. Sometimes the pole can lift up and go over the end, but other times it will try to turn the other way because of the random movement of the particles, and the net result of that would be no movement. This should not be difficult to imagine because the temperature on both sides is equal. There is going to be no net motion because you have a bunch of particles in these boxes, and by the by statistical mechanics, you should not have a net average motion. It will jiggle quite a bit since you do have this random motion as it's bumping against the panes, but it would not do what you want to do, which is to just rotate it in one direction. The reason for this is because you need to do work against the spring in order to lift the pawl to the top of a tooth so that the spring can move down and keep the pawl from rotating backwards. The chance that the energy, or that the system will accumulate the energy epsilon to get the pawl over the top of the tooth is e to the negative epsilon divided by kt, k being the Boltzmann constant and t being the temperature of the system in Kelvin. The probability that it will also accidentally go the other way is the exact same because the temperature is the same in both systems. So the number of times that the pole is up and that the wheel can turn backwards is also equal to the number of times that it can go forwards. And because you achieve this equilibrium, this balance, this causes the wheel to not rotate and do work to lift the object on the pulley.
Because it's in equilibrium,
Mhm.
and we would need an unbalanced, non-equilibrium system
To do work.
to do work. Okay.
Yeah.
Okay. So, William, we were talking about Richard Feynman's perpetual electron, if I call it theory, and is this relating to that as you see it, or is this just some of his work in general?
Not that I can tell. I don't think this relates to the electron because it's talking about Brownian motion.
Okay.
This is, and gas molecules in
Okay.
particular, which are much larger atomic particles compared to the subatomic particles of the electron and others. I do recall reading that Dr. Feynman had a discussion with another physicist named Wheeler about the idea.
John Wheeler, Princeton.
Yes,
Okay.
from John Wheeler, where Wheeler proposed the idea that all electrons in the universe are the same electron, and that's why all the electrons have the same charge, the same mass, and so forth. But I don't think that relates to the perpetual electron idea that we discussed
Sure.
in Thanksgiving.
Sure. And then, so can you expand on that conversation, as you understand it, about the what John Wheeler was talking about? That conversation that they had, as you read about it or understand it.
I don't have.
Okay. But
much
it's interesting, right? It sounds interesting.
Yes, it's
Theoretically.
yeah, it's definitely an interesting theory, especially in quantum physics. The observations are, of course, very, very difficult. There are mathematics involved behind it, probability theory, and it gets particularly difficult because at those small levels of observation, the instruments used to try and measure it,
Mhm.
they can drastically change the results that you're observing.
Yes.
If you were to think, let's imagine you have a cup of hot water and you want to try and measure the temperature of it, you'd place the thermometer in it, right?
Yes.
But when you place the thermometer
It
in
affects
it,
the temperature.
right,
Although you could make the thermometer, you could you could adjust the temperature to the thermometer separately, having it uh, close to the temperature that the liquid is, I guess,
yes,
before you put it in there.
yes, when you have a large enough system, the heat reservoir is so great that the slight temperature that is extracted from the reservoir by the thermometer to reach an equilibrium, it becomes negligible. But that is because you're working with a fairly large macroscopic system. The issue with quantum physics is that it is subatomic. It's getting so small to the point that the means to actually study the phenomenon uh, render it render it impossible to get precise data at the same time about an electron's position and its momentum.
At least with today's tools, right? With today's tools, there could be a day that we could accurately measure, but it's unimaginable. Maybe it's hard to imagine that. Maybe you don't think we'll ever be able to do it ever.
The core problem right now
Yeah.
is that electrons are very small, and in order to study its position, you need a very small frequency in order to a very high frequency, a very
Mhm.
small wavelength, in order to get insight on its position. But high frequency waves, high frequency waves, those are high energy waves, and so when they go in and interact with the electron, they will cause that electron to become very excited,
I
and
see.
because of that excitement, it increases its kinetic energy,
Sort
thus
of.
changing its momentum.
Yeah.
And that is the premise of the Heisenberg uncertainty principle, because you cannot know both the position and the momentum of an individual electron. It is possible using statistical mechanics to get a general idea of the whole system that you are working with, but when it comes to trying to extract information about an individual electron,
Hmm.
that I think at the moment is impossible and would be very difficult to try and achieve experimentally.
Okay. Um, if someone wants to learn more about that conversation between John Wheeler, or the communications between John Wheeler and Richard Feynman, how would you imagine that someone could learn more about that? Is that documented well, as far as you know?
There is a Wikipedia page, if I recall correctly, that discusses the conversation. Let me.
But could someone find the source? I mean, did they? Because Wikipedia's, I understand, people use Wikipedia, but
Yeah, I think there would. Yes, I think.
can they buy books? Can they see the source, the original?
I think the original source was a letter that Dr. Feynman wrote to another colleague where he was recounting the conversation he had with Dr. Wheeler. That should be available on a university website, if not in a library.
Yeah. So people can access it. It's accessible.
Yes, it should
And it
be
would just be
accessible.
conversations between John Wheeler and Richard Feynman.
I
Is that
think
something like
so.
that? Okay.
Or a conversation between Feynman and another physicist where he mentions the conversation with Wheeler
I see.
as It does appear, as mentioned, the sources on Wikipedia does provide the quote from that letter. It may be possible to search for the quotes used on a search engine and find a book that expands on it more.
And how about Richard Feynman's uh, theories of the perpetual electron? You were saying on Google you couldn't find anything, right? Is that correct? Or very
Everything
little?
I found related to what we just
To
discussed
this.
for this
Okay.
ratchet and the Brownian motion of the part of the gas molecules interacting with this.
Interesting. But he doesn't. Is he saying this is his perpetual electron theory, or that's a separate?
This is separate.
This is separate, but we couldn't find anything on that yet.
Not
I'll have to
yet.
look for that. That'll be
Yeah.
a fun challenge.
Yeah,
Okay,
definitely.
everyone. Was there anything else you want to add? What were your thoughts about consideration of these theories? What are your thoughts about it? Was it interesting to you to learn this?
That's very interesting. This is a very simple, very ideal system. I think does a good job of discussing discussing Carnot's principles for the laws of thermodynamics and how it applies to the work that can be extracted out of a system. This is a little more advanced, but it does provide a summary of the operation where it uses a couple of different terms and a couple of uh, concepts in statistical mechanics in order to provide a operation for a reversible system of a formula that is very familiar to thermodynamics students, where the energy of the second system over the energy of the first system is equal to the temperature of the second system over the temperature of the first system. The ratio of those two are equal, and this is taught in introductory thermodynamics classes, introductory physics classes, as a core idea behind work and reversibility.
And William, what are your thoughts about? Because when you're talking about the first and second laws of thermodynamics,
Mhm.
are these Are these equilibrium thermodynamics? Is that what we're talking about?
Yes,
Balanced equilibrium thermodynamics.
the universe tends towards a state of equilibrium and maximization of entropy, disorder, and chaos.
This is the way you're taught in school, right? This is what you're
Yes.
saying. The educational way
Yes.
teaches you. And what do you see when I say open system thermodynamics? What did you visualize when I say that? Open system thermodynamics.
Open system,
Yeah.
that is a system that interacts with its outside surroundings. A closed system is one that is entirely, or an isolated system is one that is entirely contained. No energy can get in or out, no matter can get in or out. Closed system means that matter stays in, but energy can get out. And an open system means that both energy and matter can get out. So if we were to imagine, say,
Yes.
a flask, an open flask would be an example of an open system, because you have stuff that can come out along with, say, heat that is escaping the flask.
Okay.
An example of a closed system would be a capped flask, because matter wouldn't be able to get out, but you could still have heat escape from the system. And a example of an isolated system, it wouldn't exist in reality because you always have heat escaping. But if you were to create some insulative material that could perfectly keep the heat in and prevent that from escaping the flask,
Mhm.
along with the cap, that would be an example of an isolated system.
And are the laws of thermodynamics, as you understand them, referring to a closed system or an open system?
It is referring to a closed system, but we have to remember that the entire universe is a closed system by definition, because
So the definition we're taught is that it is a closed system, and that's why we have closed system thermodynamics.
well, you can have, it gets a bit more nuanced than that, because the entire universe is a closed system, but you can have systems within the universe that are considerably more open. in biology, for example, you have cells which regularly exchange matter and energy with the environment, either molecules like
I'll be right
water
there. I'll be right there.
and sugar, along with energy like
Yeah.
ATP.
Hmm.
So the principle of of the laws of thermodynamics,
Yes.
as they apply for the universe, it's because the universe is a closed system. You're not having energy leave it and going into some other universe,
That,
to our knowledge.
to me, that implies, right. And I mean, I could say, how do we know? I could say that. I mean, we
Right.
haven't, have we left our galaxy? There's billions and billions of galaxies, and there could be many, many universes. But
There
this,
could,
you're just saying this is our theory, this is the way that we are taught in school.
yes,
And Willem, do you want to establish your education so far and what your plans are?
yes, I am a fourth year biochemistry major. I am a history minor at UC Riverside, and I am currently working to become a professional researcher in computational physics.
Okay. If we one day discovered that the universe is an open system, what would that do to thermodynamics?
It would,
Theoretically, hypothetically speaking, yeah.
uh, it would dramatically undermine the idea that the universe is a closed system and that all the energy within the system or within the universe is contained to that system. And there are other universes, there are an infinite number of universes that we need to consider. That would also make equilibration physics considerably more difficult.
It would make what more difficult? Equilibrium?
Equilibration, yeah.
Okay.
One of the theories for the
Yes.
end of the universe
Hmm.
is the idea that energy will dissipate to the point of complete equilibration until molecular motion comes to a complete stop. This is working under the assumption that the universe is a closed system.
Closed system. Because if it's an open system, that doesn't have to happen.
Right.
Interesting.
Of course, when you get to that time scale of the end of the universe, that is a huge amount of time.
Yes.
And it's worth noting, there are also many other theories on how the universe could end. One theory is continual expansion, where everything keeps getting further and further away from each other, more and more redshifted, as it all accelerates faster. Current paradigms suggest that this may be the case. There are some things which are becoming more redshifted when you would expect it to slow down compared to when the universe initially started expanding 13.7 billion years ago. But there are other theories too. One theory is the Big Crunch theory, which is the idea that after expanding to a certain point, gravity will start pulling everything in the universe back in towards a singularity. And
William, what motivates these theories that are being considered? What motivates those theories? If I could ask it that way, as you perceive it.
to my understanding, it's based on our current knowledge of the forces that govern the universe. Big Crunch theory, in particular, is mainly gravity. It's pulling everything back in towards itself. There are others, and several unaccounted for aspects of the universe, however. Dark matter is one of them, and some scientists speculate that this may cause the increasing redshift and expansion. And there's also the idea of whether or not there was a single Big Bang. Uh, if there was just a single point of expansion, because we can see some parts of the universe are redshifted, but others are more blue shifted. So, was there a single Big Bang, or were there multiple Big Bangs that happened?
And these are all theoretical. This is all theory, right?
All
Speculation.
theory.
William, is there any indication, just briefly, that the subatomic universe has slowed or sped up as it's been measured? If I say it that way, the subatomic universe has slowed or sped up. As far as you know, is there any indication that it's done that? If I just ask it that way, I'm just thinking of it that way, you know.
I'm not quite sure.
That would have to be looked into. Right.
I'm probably needs to be looked into more.
Okay. It's just the thought that comes to my mind is
Mhm.
like, are things, is the material universe as far as subatomically speeding up or slowing down? Okay, we're going to stop this stream right now. William, thank you very much for sharing your thoughts and the theories that you've learned and think about. And we will revisit you in the future, everyone.
Thank you for having me.
Thank you, William. Okay, have a great day. Let's end the stream on our page with our little experimental theory here. Okay, everyone, have a great day. Bye-bye. All right, bye, William.
Goodbye.